All right, here we go. Section 1.2, finding limits graphically and numerically. This will be, these notes will be uploaded in blank form in Blackboard if you want to follow along. You'd also need to get your calculator out because you're going to be using that as we work through this. All right, so I'm not going to take a whole lot of time. Some of this is brand new to some of you. Some of this is complete review. So let's look at this function right here. I'm going to put it in our calculator as y1. And we graph that in y1. It's going to look something like this. Sorry, a little blob there. So we are interested in what happens to this function near x is equal to positive 1. We're going to look to it when it comes from the left. We're also going to be looking to it as it comes from the right. We can also go to your table, so you can go to table setup. And you probably want your delta x to be 0.05. And if I do, it looks like here as we come in from either side, as we're coming in from the left and we're coming in from the right, our value or our function is approaching the height of 2. Excuse me, a height of 3 right there. Nope, mistake. Let's go back. Let me erase that. Not a height of 3. I was right the first time. We're going to a height here of 2. Yes. Okay? All right, so here's our definition of a limit of a function. When we say the function has a limit, we say if f of x becomes arbitrary close to a number L as x approaches c from either side, that's that left side and the right side, then the limit f of x as x approaches c is L. And here's our notation right here. All righty? All right, so we're going to move up just a little bit. Oh. All righty. Let's finding another one numerically. And in this particular function, not too interesting. Our function looks like this here, like that right here. And if, as we approach negative 3.2, we get negative 1. Negative 3.1, we have negative 1. Negative 2.9, negative 1. We have negative 1. And lo and behold, here, this limit function as x approaches negative 3 of the absolute value of x over x is also equal to negative 1. Okay, not too snazzy there. Pretty straightforward. Alrighty, and then here I've already graphed it for you. So let's take a peek at this. We're looking at this function at the limit of f of x as x approaches 1. It's a piecewise function. And we look at this, and the question always becomes, let me erase here over here. The question always becomes, what's happening as I approach from either side? So what's happening as I approach in from the left? What's happening as I approach in from the right? If the function is approaching the same height, okay, if it has the same behavior, and we look at what the right-hand limit and the left-hand limit is doing, if they're equal to the same value, if they're approaching the same value, and in this case, we have the limit of f of x as x approaches 1 is equal to 3. So the existence or non-existence of f of x actually at x equals c has absolutely no bearing on the existence of the limit of the function as x approaches c. To the next page. I'm going to zoom in just a tad, try to keep it straight. All right, so there's 3 ways to approach finding a limit. You can do the numerical approach, which is construct a table of values. Calculator is always helpful here. You can do a graphical approach, which is draw a graph by hand or with the TI-83 or 84 or Inspire, whatever your calculator of choice is, or the analytical approach, which is the used algebra or calculus. All right, so when limits that fail to exist, you can typically figure that out when you look at the picture. All right, so let's look at this picture here. We have a piecewise function. Kind of easy here. We have, it's a parabola when x is greater than 0, but we have an open circle right there, open hole, because it's not defined at 0. And everywhere else when x is less than 0, we're down here at negative 3. We also intersect here at negative 3 on the x-axis. And we have, oh, that's not very straight, but we'll go with that. We have a line that looks like that. All right? Now, remember, does the right-hand limit equal the left-hand limit? That is, graphically, as I'm coming from the left and I'm coming from the right, what is the function doing? Well, as I come in from the right, this function is clearly approaching 0. But as I come in from the left, the function is approaching -3. So since they do not exist, we say here that the limit as x approaches 0 of f of x does not exist. And this abbreviation, does not exist, is perfectly acceptable. You don't have to spell it out. All right? Then we have some things that are called unbounded behavior. And so if I graph those functions, so if we look at the graph here, we know that we are undefined at 0. So we have a little asymptote there. But our graph, as we come in from the left side, blows up to infinity. And as we come in from the right, it also goes up to infinity. All right? Now, in math analysis, or pre-cal, we said this function did not have a limit. But what we're really looking in calculus is the behavior the same from the right and from the left? Okay, so is the behavior the same? The behavior of the function, like what is the function doing? So when we say right-hand limit and left-hand limit, right here, both of these limits coming from the right, coming from the left. So if I'm coming from the left, I'm coming from the right, both of these pieces of our function approach the same behavior. So in this case, we say the limit is infinity. I know in math analysis you would say that that limit doesn't exist, but that behavior from the right and the behavior from the left is the same, so that we say that that does exist. Alrighty, here's an interesting one. Very, very interesting. So you got to get your calculator out. I want you to do a couple things here. All right? In y1, I want you to put in this function sine of 1 over x. All right? Make sure your mode is in radians. Okay, radian mode. I want your x min to be negative 2.5, your x max to be 2.5, your y min to be negative 1, your y max to be positive 1. All right, so go ahead and graph that. You do one more thing. Okay? You're going to go into zoom. Okay, third button in the middle, up there at the top. You're going to go into zoom. Oops, I don't know what that is. You're going to go to zoom. And you're going to toggle over to memory. Okay, toggle over. And you're going to go down to number 4, which is set factors. All right, go down number 4. All right, you want your x fact, which is your x factor, to be 4. And you want your y fact to be 1. Then what I want you to do, once you graph it, hit zoom in. Okay, go down number 2. That's number 2 in your zoom. Okay? And I want you to zoom in a bunch of times. Okay? A bunch. And I want you to tell me, think about this, we'll talk about it in class. Does the limit as x approaches 0 of sine 1 over x exist? And remember that the right-hand limit has to equal the left-hand limit. And it has to be the same. So tell me what's going on there. All righty? Lastly, I'm going to zoom in just a little bit here. All right? Use the graph to find the limit. If the limit doesn't exist, explain why. So the biggest thing you want to remember right now is, does the right-hand limit equal the left-hand limit? If it does, a limit exists. If it doesn't, so if the right-hand limit does not equal the left-hand limit, then the limit of your function does not exist. All right, and finally, last thing I want you to do, a little crooked here. There we go. All right, as you have this graph here, I want you to find there's three functional values. Functional values are A, C, and E. How high is the graph, or what is the value? And then B, D, oh wait, there's another G, functional. And then B, D, F, and H are limits. You're going to use this. Don't worry about this. That just says this is where the picture came from. All right? You're going to find the limit, and we'll go over this first thing in class when I see you next.